Okay, I hope you are energized after coffee, sugar, and caffeine in your coffee. So let's start now with Dominic's. This would be the fourth lecture of this mini course.
Thank you. Is this thing working? Can you hear me? Yeah. Pretty okay. Okay, so let me remind you that the problem which I introduced to you yesterday, which also was repeated today, he called it P3. So our problem we want to solve is embedding abstract Riemannian manifolds isometrically some Euclidean space. So the problem is given Riemannian manifold, say n-dimensional smooth manifold, nice Riemannian metric on it, find an embedding into some Euclidean space, and I include the dimension of this Euclidean space as a parameter. So find a Q bigger than or equal to n plus 1, and an embedding. So a C1 map with differential with full rank at any point, taking this manifold into Euclidean space RQ, such that it preserves the length of any manifold. So take a curve here, compute the length with respect to G, length of image curve, the length has G. And we saw that this condition is equivalent to the condition that the pullback metric or induced agrees with G. I kind of ran results here. This over here in local coordinates, you end up with a finite system of PDEs. You have exactly, so this is a system, as Govind said, system of, and I call this number n star. So exactly n times n plus 1 divided by 2 nonlinear PDEs in Q unknowns. And so it seemed natural to try to look for solutions U where Q is exactly n star. So for example, 2, it would be R2 into R3. So two-dimensional manifolds in R3. And I showed you some results which seem to run into a dead end when asking this question. So I showed you that there doesn't exist a C2 isometric embedding from the flat 2 torus into R3. There doesn't exist a C2 isometric embedding hyperspace to R3. And okay, for the positive curvature K, C2 you have, so if this is a nice, let's say, if this is the 2-sphere and you have a metric on it with positive Gaussian curvature, we saw that there is a unique solution of this thing. And then I stated the very surprising theorem of Nash and Kuiper, which tells you that you can always solve this system. And sometimes, or often even when Q is very small, so Q, so recall the Nash-Kuiper theorem, I think, I don't remember. This was Nash-Kuiper. If Q is that Mn compact, smooth, G is just continuous, and Q only bigger than n plus 1, that if you give me a map from this manifold into Euclidean space RQ, which somehow shrinks all the lengths, so if U is short embedding or immersion, so somehow I can put this manifold topologically in Euclidean space RQ, plus I can make it such that all the lengths are too short. Then in fact, in any small neighborhood around this short, I can find a map which is length preserving. So given any short map and any epsilon smaller, bigger than 0, there exists E, which is a C1 map from M into RQ, which is an isometry. Okay, V, so if I start with an embedding, V can be chosen to be an embedding. I start with an immersion, I end up with an immersion. And recall these two things differ by embeddings are injective. So such that it's a solution, the induced metric of V is exactly G, and I'm very close to U. Another way of saying it is that any short embedding can be uniformly approximated by solutions. So just choose epsilon 1 over k, you find a sequence of solutions approximating the short. So this is the Nash-Kuiper theorem in 54 and Kuiper in 55, lowering the codimension by 1. And I gave you a couple of reasons why this is a very interesting and surprising theorem. And is there only 2 over here? No. And so what I want to do today is to give you a proof of an easier version of this theorem. So we start 1.4 was the proof of Nash-Kuiper. Simplifications. So 1.4.1 was simplifications. So let me stress, theorem was not surprising or influential because of the result. It gives you the existing isometric embedding of the flat 2 torus in R3. It gives you the C1 isometric embedding of the 2 hyperbolic space into R3. It gives you the reduction of any sphere into any small ball, isometric reduction. So the result is very interesting, but the technique which Nash used or invented to prove his theorem was super influential. And so this is why I want to show you the proof, because it's, the idea is pretty, also the technical too difficult, but still they're a bit difficult. So in order to deal with this difficulty, I want to make some simplifications, keeping the ideas, but getting rid of some of the difficulties. And the simplifications is that, first of all, we are not a full compact manifold, but simply one coordinate chart. So we had, so let me simply state the theorem which I want to prove to you. Maybe 6, so easier. So I want to simplify folds to being one chart. I want to simplify to codimension 2, and I want to simplify to immersions. I want to show you that an injective map, but it's not too hard. So what I want to show to you is the following. Let omega is simply a nice, smooth, bounded subset of Rn. Open. Your metric is now not 2 tensor, but it's simply a matrix field. So G, I take it C infinity, just a smooth function from omega bar to the space of symmetric matrices of size n by n, positive definite. That's my Riemannian metric. And U is, let's say it's a infinity map from omega bar into Rn plus 2. So here's one simplification, n plus 2. Here's another simplification. This is my M. Strictly short immersion. Then I want to show you that for any epsilon bigger than 0, there exists a V C1 omega bar into Rn plus 2, such that its induced metric is exactly G. It's isometric. In particular, it's an immersion, because this is non-degenerate. And it's arbitrarily close. And V minus U 0 is less than epsilon. So it's easier, or it's of a local version. And you can imagine that getting the global version, you just take a bunch of coordinate charts and patch together. I mean, okay, it's in the construction. You need to patch together the construction. So it's a bit more difficult technically, but it's not too far to go if you know the local version. Okay, any questions at this point? So today, let me first give you the idea or the heuristics of a proof of this theorem. So what I want to do is I start with a map U immersion, which is strictly short. All the lengths are too short. And I want to find a map where all the lengths are. So I want to stretch out this map. Nash realized a good way to do it. So let me start over here with the heuristics of the proof. So given U strictly short, so Nash realized that a good way to stretch out a map is do this iteratively and always stretch out a little bit, but not too much. So build a sequence of short maps, of strictly short maps, short immersions, UK, and okay, U0 is U. That getting less and less short. So in the end, I want such UK transpose DUK to G. And it's Cauchy in C1. It's Cauchy in C1. So I have a limit. And this limit, so I have a limit V, which is a C1 map. And I'm converging to the C1 map in C1. This sequence over here is converging in C1 to V. So in particular, all the derivatives are converging. But the derivatives to G. So if I take the limit over here, I will see dV transpose dV. Limit of this sequence will be my solution. Okay. Short immersions such that, so in particular, UK plus 1 much less short than UK. And so the question now is how to build the map UK plus 1 if I'm given UK. And I want to do this, I want to stretch out this map, but I want to stay very close. So in the end, I want to end up within the epsilon neighborhood of my starting map. So in particular, at any step of this iteration, I want to stay very close. So maybe epsilon 2 to the minus k. Okay, and the question is how to stretch out a map while staying epsilon close. And Nash realized that a good way to do this is to add spirals. So Nash adds spirals. And okay, in the work a year later by Nicolas Kuiper, with lower codimension. So what Kuiper did is not adding spirals, which need 2 codimensions, but corrugations, so little waves. Kuiper at corrugations. But they're a bit more complicated. So adding spirals means I get my map UK and I perturb this map by simply adding to this map a spiral. And the basic building block or the basic ansatz is assume I'm given my map UK. Let me call this for now U. Assume given U map. What I want to do, so let me picture this. I have my map U over here. So what Nash does is pick two vector fields which are normal to U. Vector fields, one is zeta, and the other one is psi. So these are both orthogonal to U, or to the image of U, and they're also orthogonal to each other. So orthogonal over here, orthogonal to U. Yeah. And what I do is simply add a spiral around U. So now my V. So I'm perturbing this map U by adding a spiral, and I get a map V. So let me draw U again. And my V will look like a spiral. So this is my V. That's the picture. And as I tried to explain yesterday, if you look at the distance between 2 points on U, let's say this is my U of P, and this is my U of Q. Q is bad. U of P prime, thank you. So I have 2 points. Distance over here is like this. And now if I look at the same thing for V, so here's maybe this is my V of P, and this is my V of P prime. And on V, the distance between V of P and V of P prime is now much longer because I'm doing all of this telephone cord thing. So this spiral should increase length. Okay, the general ansatz of the spiral is as following. So I need these two orthonormal vector fields. So given U, let zeta omega be such that zeta and psi are orthogonal to the image of U. They're orthogonal to each other. So psi times zeta times psi is 0. And they have length 1. So these are two ingredients for the building block. What I also need is some frequency spiral. So I take a large frequency. I need a direction. Eta is a direction. And you cannot really see this in the 1D picture, but it's a direction in which I'm, with the answers I'm going to write down, I'm able to increase the metric in a direction which is defined by eta. This is just a unit vector. And I need an amplitude function. So A is a smooth function. Define my new map V, which is just the old map. Let me write all the x's, maybe V of x. I define it as U of x. And now I add this spiral, which is simply A of x, my amplitude divided by lambda, big frequency. And now I do simply a sine lambda x dot nu zeta of x plus cosine lambda x dot nu psi of x. This is my ansatz for the spiral. Let me call this the perturbation W associated to A, eta, and lambda. Perturbation W associated to A, eta, lambda. And all I need, given U, is two normal vector fields. These are determined by U, and A I choose, lambda I choose, eta I choose. Okay, and the picture is right there. So that's how V should look like, or how you could think about V. The eta you don't see in one dimension because yeah, S0 is just, yeah. Okay, so from the picture you would think that this perturbation, or for this map, the induced metric is larger. Because you see the lengths get longer. Let's compute what happens to the induced metric of V. Well, what is the induced metric? Well, I can simply compute it by computing the derivative, taking transpose times derivative. So let's compute the derivative of this map. This should increase lengths. Indeed. Let's compute what the derivative of V is. So derivative of V, let me drop the x's. So I see the derivative of u, du. And then I have a couple of terms. So derivative could hit A, it could hit sinus, the sine, it could hit the normal vector field, and also cosine and the normal vector field. So the largest term is when the derivative hits the sine or the cosine, because then a lambda pops out and cancels this 1 over lambda. So because, okay, first, because I'm thinking about lambda being extremely large, you can see that the C0 norm, or like the distance from V to U, this has size 1, this part. These are orthonormal, these are sine and cosine. So the distance between is like A divided by lambda. So if I choose lambda super large, this will be less than epsilon, depending on A. So I'm staying back, and I want to see what happens to the induced metric. So derivative over here, as I said, the biggest part is when derivative hits sine or cosine. Lambda pops out, cancels this 1 over lambda. So what I see is A, then I see the cosine. Let me not write this thing over here. I see zeta tensor. When I take the derivative of this function, I get exterior derivative, and then I get the derivative of the argument over here, which gives me an eta. This is cosine in the direction of eta. So when I take derivative of x dot eta, I see exactly eta. And okay, here minus sine psi tensor eta. Maybe do this as an exercise. Are you familiar with this notation over here? So if I have two vectors in N, maybe over here. So if A and B are simply row vectors in Rn, what I mean by A tensor B is the matrix with entries. So this is a matrix with entry A tensor B, ij entry is simply AI bj. Or in other terms, if you like to think about this, it's the matrix which you get when you do the row vector A times the transpose of B. So A is over here, and B transpose is over here. And then down here is A transpose B. Figure it out, let's do a component. I mean, okay, just look at what this Jacobian matrix is and compare the entries, you see exactly what's over here. So this is the largest part. And then the other things I don't really care. So I simply get, let me still write it. So this would be the plus 1 over lambda sine when the derivative hits either A or zeta, plus cosine when the derivative hits either A or psi. But no matter what A and psi are, I simply choose lambda large enough. I make this very small. So this term over here is an O1 over lambda term, very small if lambda large. Okay, so we computed the derivative. Very good. Let's look at what the induced metric is. So let's take a transpose of this guy and times itself. So imagine the whole thing over here transposed. So a t everywhere. Recall that. Can you read the blue? Okay. So just recall that if you take, maybe let's. So as a formula. Thank you. So just computation, if you take this matrix, take the transpose of this matrix, you see exactly B tensor A. So A tensor B transpose is simply B tensor A. If you look at the transpose of this term over here, you see the same simply with eta and zeta swapped. And what I also need, this product, dv transpose times dv, I need to somehow do matrix product of these guys. And this is another formula, A tensor B times C tensor D is the same as the inner product between the vectors B and C. So this is a matrix, the matrix multiplication over here. It's the same as the inner product between B and C and the matrix A, which is easy to see if you write it like this. So using these formulas over here, you can check that following holds if you compute the induced metric. So it follows that dvt times dv. So you need to transpose all of this and multiply it by itself. So the first term you see is dut times du. Then you see dut, so it's the old induced metric. So I'm writing dut times itself. Then I have a term which is dut times this term over here. And now observe when dut hits this term, which is the largest term, what's happening is that dut hits zeta or psi. And zeta and psi are orthogonal to u. So dut hitting this term is 0. Right? So plus, let me do dut times a cosine psi tensor e minus sine sine psi tensor eta. This is just 0. Since these are orthogonal to the image of u. So I chose it exactly in this way. Okay. Then I have a term where the dut hits this, but it has a 1 over lambda in front. And I don't care about terms which have a lambda in front. Okay? So the next term is when this large term hits itself. So when this term hits itself with the transpose, what I see is, I see the transpose eta, so transpose eta tensor zeta hitting itself gives me the inner product between zeta and itself times eta. And okay, I have a unit normal vector. So the inner product between zeta and itself is just 1. Meaning when this term hits itself, I get a cosine square times 1, times eta tensor eta. When this term, or this term, hits this term, I get 0 because I see that the zeta on the psi, orthogonal. So I have no cross term over here. When this term hits itself, same thing, I get a sine squared eta tensor eta. So in total, this term hitting itself gives me an a squared, and then cosine squared eta tensor eta, sine squared eta tensor eta. So in total, this guy hitting itself is a squared eta tensor eta. Maybe exercise. So these are not so difficult. I mean, the computations are not so difficult if you take a couple of minutes to try to make them. And then I get all terms where du hits this one, where this hits this one, where this hits itself. All of it has a 1 over lambda in front. I get a term which I don't care so much because I can make it as small as I want simply by choosing lambda large. So what I see is that the ansatz spiral indeed increases the induced metric as compared to what I had before, namely by this piece. It's a positive definite piece, a squared eta tensor eta. It increases the induced metric exactly in the direction in the space of symmetric matrices by a squared up to a small error. So spiral allows to increase induced metric by this piece a squared eta tensor eta. And this was this is what I don't think Nash actually called it this, but it was called in all of the works following Nash. This piece over here is called a primitive metric. Primitive metric up to small error. Oh, 1 over lambda. I can make this as small as I want just by choosing lambda as large as I need. So this gives an idea of a procedure on how to stretch out my maps. I simply add these spirals, and I gain these pieces a squared eta tensor eta. Now I have the freedom of choosing a, I have the freedom of choosing eta, I have the freedom of choosing lambda. So what is a good choice? And here the Nash lemma comes in. So idea for procedure. Or for stage. Stage is what Nash called the construction of UK plus 1 given UK. And it's exactly how to stretch out UK in a nice way to gain a map which is less short, but still short. This is what he calls stage. Construction of UK plus 1 given UK. I now have this building block, one of these spirals, and I know the effect of such a spiral is simply to increase the map. I mean, if I add such a perturbation, I increase the induced metric by a primitive metric of this form plus a small error. So what I do now is simply look at the distance still to go which is captured by the residual, as Gorman called it yesterday. So decompose the metric defect or residual namely G minus duk duk. Short, so this is a positive definite matrix, and it captures exactly how far uk is from being isomorphic. It's a positive definite matrix, and I know I can add, by using these spirals, I can add these pieces, so I want to decompose what I still need to go into these pieces in primitive matrix. And this is called a Nash lemma. So G minus uk tensor transpose duk. I want to decompose it into a sum, finite sum. Okay, now let's use L maybe. Eta L, tensor eta L. L is from 1 to some big number n. So Sn minus 1. And these are C infinity functions. So this is called a Nash lemma, what the government was talking about before. I heard that green is not good. Where's my yellow? Here. So this red is not good. So this is the Nash lemma. So it's not so easy. I mean, you could say, okay, I have a positive definite matrix over here at any point x. I can simply diagonalize it. Then I use computations over here only work if these are not depending on x. So simply diagonalizing at every x would have these unit vectors be depending on x. And then so here I would get a derivative on eta. Doesn't work. I get another term which is large. So the crucial point is that these are fixed for every, I mean, these are fixed unit vectors, and this over here, coefficients over here, depend on x. Okay, once I have this decomposition, I simply add these spirals, one for each primitive metric. So second, perp iteratively set, let's say UK0 is simply UK, and I define UKI to be UKI minus 1 plus the spiral over here, W, which is corresponds to AI, it corresponds to theta I, and it corresponds to some lambda I, which I simply, at every I choose one. So this is for I equals 1 to big N, lambda I to be chosen. Right, so the ingredients in my perturbation here, they are the normal vector fields. They are determined by the map which I'm already given. So UK I minus 1. I compute the normal vector fields, and then I choose the coefficient A over here to be exactly the A Okay, now I chose I, but I chose the ith AI over here, and I choose the eta to be the eta I corresponding to this one. Okay, and when I do this, it should follow that the induced metric of this guy is exactly the induced metric of this guy, plus AI squared eta I times their eta I, plus a small error. And so, let me maybe go, let's start again over here. And in the end, I set UK plus 1 to be the nth perturbation. Yeah. And please interrupt me if something is unclear at this point. Are there questions? So setting UK plus 1 to be UK big N yields that the induced metric of this UK plus 1 is simply the old one, plus K plus L from 1 to big N of the differences. So DUK L T DUK L minus, so telescopic sum over here, L minus 1 T DUK L minus 1. Right, telescopic sum, I see, well, yeah, should be correct. And now my computation over here, my heuristic computation shows me that if I do one perturbation, so if I do one perturbation over here, the difference in the induced matrix, so if you do dVt minus dUt, you see exactly A squared eta times or eta plus this small error. So in this sum, what I see is exactly duk plus sum L equals 1 to n of A L squared eta L tensor eta L, and then plus a small error, which is very small if I take the frequency at this stage L very large. Maybe let me write this as a separate sum. And now what is this guy over here? Well, it's the sum of all the primitive metrics, but they come exactly from decomposing my metric defect. So the sum which I'm getting over there is exactly the distance between G and the induced metric of U. What I see over here is simply, so this is G minus duk by construction. So adding this primitive matrix over here, I see I'm G up to this small error. So this is G plus all these errors. Okay, I feel I went a bit too fast. So the strategy over here is you're given map UK, you look at the induced metric, you see that it's short. So the distance between G and this induced metric over here is some positive definite matrix field. What I want to do is write this positive definite matrix field as a finite sum of small primitive metrics, because I know that by a spiral of this form over there, I can make the induced metric larger exactly by these pieces. So then what I do is iteratively adding, which should increase the induced metric exactly by this piece up to a small error. So this is what I do here. I start with the map UK. Then I do UK1 is simply UK plus this first spiral. I add exactly this spiral over here with A1, lambda 1, eta 1. And these are the vector fields which are normal to UK. If I do this, compute the induced metric of UK1, I see it's the old induced metric plus A1 squared eta 1 plus some small error. Then I have UK1. Okay, let's add a second spiral corresponding to A2, eta 2. And I do this until I get to the perturbation corresponding to AN, eta n. And if I look at the final map, which I now call UK plus 1, if I look at the induced metric, I can write it using a telescope sum over here, simply as the old induced metric plus the difference in the induced metrics at every small step. And as I see from the computation over here, up there, the difference between the induced metrics is exactly the primitive metric A squared eta tensor eta plus a small error. So I see, so this part over here is exactly AL squared eta L plus the small error. Okay, I take the sum apart, and I realize the sum of all these small primitive metrics is by construction exactly G minus the induced metric of UK. So if I add the induced metric over here, I see that, okay, these two cancel. I'm left with G plus this small error. So I'm almost an isometric embedding, weren't it for this error over here. So the spirals give a good way of increasing the induced metric plus a small error. But this I can simply make small by choosing lambda very large at every step. Lambda 1 large, lambda 2 large, lambda 3 large. Okay? So now we have a slight problem. We are almost G. I mean, I can make this as small as possible. But this might be a positive definite tensor, or I don't have any control over these error terms. So what I lost is the information that this is a short map. I don't know that this is negative. So, and we'll deal with this in just a moment. But this is the strategy. So the question over here, to make this heuristics rigorous, is first we need this decomposition over here. The question first, Nash lemma. And secondly, how to make UK plus 1 short. Because then, if this is a negative thing over here, or if I have some space, if I know that this is still below G, I can make it as small, as close to G as possible, simply by making this very small. I can simply repeat the process. I get UK plus 1, I decompose it, I add the spirals, and I get UK plus 2, which is even closer to G, but still short. So then I just repeat the process and show that it's converging. So 3 y UK plus 1 UK Cauchy. And just observe over here. So why should it be Cauchy in C1? So I know I'm staying very close to my map A just by choosing very large. Each step, the distance between V and U in C0 is bounded by the size of A, which is, say, controlled, and divided by lambda. So choosing lambda large enough, I make smaller than epsilon. And I do this for every step. So I can guarantee that in C0, I'm very close. But still, I want somehow that UK is Cauchy in C1. So also the derivatives should remain close. And why is this the case? Well, if you look at the distance between the two derivatives, you see that this term is no problem because I just choose lambda very large, depending on all these terms over here. Why is this small? Well, if you look at the size of this term over here, the parenthesis, everything inside the parenthesis is of order 1. Like this is length 1, this is unit vector, cosine, sine. So what's the size of A? Well, what's the size of A? We can compute the size of A by looking at this formula. A is roughly, so these are unit vectors, so simply taking the trace of this equation over here, you can see that A is roughly the square root of the distance over here. Right, so the C0 norm of AL is roughly the square root of the C0 norm of this guy. And this is going to 0. So I'm constructing a sequence, or trying to construct a sequence such that this is going to 0. And okay, I'm constructing it such that it goes to 0 in a summable way. Let's say exponentially. Then I see that A also goes to 0 exponentially. So in particular, distance between the derivatives over here goes to 0 exponentially. So therefore, it's a summable sequence. Therefore, it's Cauchy. This is the heuristics, and I'm going to make this more precise in a second. Any questions for the plan? And the plan, so once again, plan is we want to construct a sequence UK of short maps which get less and less short. And we do this by stretching the map UK out in this controlled way, namely simply by first decomposing into a sum of primitive metrics, and then for each primitive matrix, adding a spiral with the appropriate frequency, with this amplitude, with this direction. Okay. So first, let's, okay. Yeah, that's the general strategy. So let's try to make this rigorous. Fine with this? Okay. So how should we decompose a metric into primitive metrics? And a crucial point is that these primitive metrics, they have the form of a matrix which is a rank 1 matrix, and a coefficient which is a function, and it has a square over here. So it's a positive function, which is smooth. And what we'll first do, which is a local decomposition. So first of all, okay, so 1, 4, 3, the Nash lemma. I'll give this a number. So lemma 1. I probably screw up my numbering. So I had theorem 1, 5 or so. Let's do lemma 1, 6. And this is a local decomposition. And let's first forget about the dependence on x over here. Let's simply think we have a fixed positive definite matrix over here. And I want to decompose it into a nice, into a finite sum of primitive metrics of this form. And the following lemma, so let me first state it and then comment it. So I'm saying that there is this constant, R0, which only depends on the dimension n, such that the following holds. So there's this constant, forget about this for a second. There are linear maps, L1 to Ln star, from the space of symmetric n by n matrices into R, and unit vectors eta 1 to eta n star. N star was this number n times n plus 1 divided by 2. These are unit vector, such that the following holds. So I want that eta I tensor eta I is a basis for the space of symmetric matrices. So I can write any symmetric matrix H as a sum, and these are simply the coefficients of H in this basis. So I write L, small l, of H eta L tensor eta L. L equals 1 to n star for every H in symmetric matrices. So right now I'm just saying I can choose a bunch of unit vectors in the number n star. I mean the number is n star, such that eta L tensor eta L, the collection, is a basis for the space of symmetric matrices. And as a basis, it comes with these linear maps, which give me the representation of any symmetric matrices in this basis. I'm not saying much. You can easily choose these vectors. So what I'm saying over here is that there exists this number, which depends on n because it depends on the identity matrix of size n. And when you're R0 close to the identity matrix, these coefficients over here are actually positive because I want positive coefficients. I want A squared. So n such that LK or LL of H are bigger than or equal to R0. So this is, the only point is that's strictly away from 0 for any H and n such that it's less than R0 from the identity away. So I'm choosing a nice basis of the space of symmetric matrices, which has the property that in the neighborhood of the identity, so this is my space of positive definite matrices, I have the identity sitting here. I have a ball of size R0, such that whenever I'm in here, my decomposition with respect to this basis has a positive coefficient for every L. Okay? Fine with the statement so far? So let me quickly, this is basically linear algebra, and it's not so difficult. So let me go through this rather quickly. And you see that the number of primitive metrics over here, somehow this is a good number. I mean, it's exactly the dimension of the set of symmetric matrices. So this number over here, the decomposition into primitive metrics, I might be able to hope that this big N over there is this number n star. And in fact, you can tweak your iteration most of the time. So let me prove. So let's start with denote. So let S be the set of matrices of the form EI plus EJ, tensor EI plus EJ, going from 1 to n. Where these are the standard unit vectors in Rn. So, diagonal matrix, or the matrices I is equal to J. And then I have combinations of the diagonal matrix plus the guys which has a 1 in IJ and JI. So in particular, since EI tensor EJ plus EJ tensor EI is in the span of S. So I can, this matrix which has a 1 over here and a 1 over, let me do, so this is I, this is J. And then I have a 1 in I and J. So these guys are in the span of S. So in particular, S spans the set of symmetric matrices, because these guys span the symmetric matrix. So this is for every I1 less than or equal to Ij less than or equal to N. S, or the span, or the symmetric matrices, are contained in the span of S. I can generate any symmetric matrices simply by looking at the coefficient over here, taking linear combinations of these guys, but these guys I can get linear combinations of these guys. And the nice thing about these guys is that they exactly have the form vector tensor vector instead of this sum over here. So they have exactly the form eta tensor eta. Okay, they span, and if I count the amount of, or the number of elements in S, it's exactly n star. And since the number in S is n star, this means that S is a basis of the space of symmetric matrices. Okay? And now I just relabel them, relabel S to be Fj, or Fl tensor Fl, L equals 1 to n star. Fine, I have a nice basis of my space of symmetric matrices of the form eta tensor eta. Well, but at the moment they're not normal, so I'd call them F. They're not normalized. They have, sometimes they have length 2 or square root 2. So at the moment, let me call them F. And now look at this matrix over here. Consider the matrix. So I want to normalize them properly. And I do this by looking at the matrix M, which is simply the sum of all L equals 1 to n star. And now an exercise for you guys. Prove that this exercise M is positive definite. Very, pretty easy. Pos definite. In particular, I can find, so this is another exercise. I have a positive definite matrix. I can find an invertible matrix L, such that if I conjugate M with this invertible matrix, I get to the identity. So there exists L in GLN, L transpose is the identity. You simply diagonalize, bless you. If you diagonalize M with the orthogonal matrix, you end up with a diagonal matrix with positive entries on the diagonal. Take the matrix which is 1 over the square root of each entry, and then compose these guys. And this is your L. Okay? And now I get my coefficients, or my unit vectors eta, simply by this formula. Observe that the identity is LMLT, which is the sum of L, so small l from 1 to n star, of LFL tensor FL, and here LT. And now again, exercise, show that this is the same. So exercise, or convince yourself that this is the same as the sum L equals 1 to n star of the vector, which is LFL, tensor the vector, which is LFL. And now I just normalize these vectors, and this will be my eta. So this is the same as L equals 1 to n star of the size of LFL squared, and now LFL divided by the length of LFL, tensor LFL divided by LFL. Okay. And now these guys are my eta. Denote, define eta L to be LFL divided by LFL. And since L is a nice invertible matrix over here, since L is in GLN, the set eta L is still a basis for the symmetric matrices. Right, my FL, tensor FL, was a basis. Now I'm just doing the conjugation with a nice invertible linear matrix. And okay, a scale. I still get a basis. Yeah? Okay, so I have, in particular, these are unit vectors. I have a basis of the space of symmetric matrices. This gives me a set of linear maps, L1 to Ln star, just from the fact that this is a basis. And there exists L1 to Ln, linear, such that blah, blah, blah. Okay, so the first one is done. I constructed my nice basis N1 to N star, eta 1 to eta n star, and I got these linear maps over here, such that I can write any symmetric matrix as a sum of these basis elements with the coefficients. The existence of R0 is simply by continuity, because if you look at so existence of R0 by continuity and the fact that if you look at the coefficient of the identity, you see it's the square of LFL, which is a strictly positive number for LEL, for any L. So here's eta tensor eta. I write identity in this basis as the linear combination with these strict coefficients. And the fact that LL of the identity is L of FL squared, which is strictly larger than 0 for any L. Okay. So I have to hurry up a little bit. Is this proof clear? I'm just constructing a favorable basis of the space of symmetric matrices of the form eta L tensor eta L. It's a basis, so it has some linear functions which give me the coefficients of any symmetric matrix with respect to the spaces. And these coefficients are positive for the identity, strictly positive. So in the neighborhood of the identity, they have to be strictly positive. So there exists this small R0, such that in the neighborhood, I'm strictly positive. Now, of course, there's nothing special about the identity over here. I could do this for any positive definite matrix. So there exists for any positive definite matrix, there is a small radius which depends on this positive definite matrix, and, okay, L1 and eta 1, such that in the neighborhood of this positive definite matrix, I have a favorable decomposition with positive coefficients. And then simply by covering, I can see that if I have a compact set, so by covering, if I have a compact set, so this is my cone of positive definite matrices. If I have a compact set K of positive definite matrices, I can always choose a bunch of positive definite matrices, which is, for example, the identity. Maybe the identity is in there, so I have my ball R0. Then I choose a bunch of different positive definite matrices. All these comes with a small radius R0, such that in this neighborhood, I have a good decomposition of all these matrices. And now I just cover my set K with finitely many such balls. And I get this finite number of unit vectors eta n and finite number of linear maps L1 to L whatever, such that, and then, okay, I do a partition of unity. Let me not get into this. But I get the following corollary. On 7, a decomposition. So for every compact set K, in the set of positive definite symmetric matrices, compact, there exists a number n. It's a natural number which depends on the compact set K, because somehow it's telling me how many balls I need to cover this compact set K. So it's a number, finite number, which depends on K. And linear maps. And vectors eta 1 to eta big N. And smooth functions A1 to AN. These are smooth functions on K, or rather on somehow an open neighborhood of K, such that the following holds, such that I can write any symmetric matrix in K as the squared of H eta L tensor eta L. For L going from 1 and now to this big N. For every H in K. Okay? So this is just a covering argument. But, and very important piece. And such that for every H, at most, so see here, I'm given a compact set K, and depending on this compact set K, I get a number N, and all my unit vectors, so from 1 to this big number N. But in fact, you can show that at any point, H in K, at most, a constant which only depends on the dimension of terms over here are non-zero. Doesn't depend on K. It's just how you do the covering. I mean, the local decomposition over here gives you at any positive matrix, you get a small ball, such that in this small ball you have a nice decomposition. And now at any point, I mean, you have all these infinitely many balls, and you need to choose a smart finite covering. And you can do this smart finite covering simply by, I mean, I think you believe me that I can do this covering in such a way such that at any point I don't see so many intersections of these balls. I see at most a constant which only depends on the dimension of intersection. So at most, let me call this small c, which is a constant only depending on the dimension n terms are non-zero in the sum. And this is actually very important for the proof. In the sum are non-zero. And the proof is simply a covering argument, as I said, at any, I mean, you do this lemma over here, not for the identity, but for any positive definite matrix. You get at any point in K, you get a small ball such that you have a nice decomposition there. You get a covering by all these balls. You choose a nice subcovering, and then you just do a partition of unity. And these AL squares are basically the square root of the LLs. And I can take the square root because in the balls I'm bigger than 0. And so I'm a smooth function. The square root is a smooth function if I'm away from 0. This come across? So all this work over here is to say I want a nice decomposition where these guys are smooth functions which have the form a squared. To have a smooth function, I mean to have that this is a square of a smooth function, I need it to be positive, and then I just take the square root of this positive function. This will be a smooth function because this is linear. I take the square root of a linear function, I'm a smooth function, if the smooth function is away from 0. And now, in any small ball, I can take the square root, and I just patch all these together with a partition of unity. So maybe proof as an exercise, or I can also do it in the notes. Yeah. Say again? Yeah. It's very similar. So the general case, you just do, you do all of this in charts, and then you patch together by a partition of unity. You get a larger n, because you need to cover the manifold. But the same thing is true. You get a larger n, but still at most a constant which only depends on the dimension n of terms are usually will be non-zero. Yes, but there's not much. There's some technical difficulties in making this. Not much in making this work on manifolds on the full manifold.
Sorry, this is the very loud one. So a follow-up is, for particular manifolds where you have a better decomposition into sets, like where you know that there's a bound in the Cn. There are these notions of Nagata dimension and finite asymptotic dimension. So those would actually be very useful here, because then that would give you a bound on the embedding dimension. Is that correct?
Not only the embedding dimension. So actually it doesn't, so for the Nash-Kuiper theorem, it doesn't matter at all.
Okay.
But, until a few years ago, it mattered I might be able to show you this tomorrow. It really mattered concerning the regularity of the embedding which you get. If you have a larger n, your embedding will be worse. But this is not true anymore since 2021 or 22. So there's a more sophisticated way of doing the construction on a full manifold, which somehow tells you that if you do something in a chart, then you can do the same thing on the whole manifold, and it won't affect the regularity. Just the plain vanilla approach of doing something locally and then trying to extend it by using charts, it will get you a worse regularity of the final embedding if you just do it, as you would, okay, the regularity I'm talking about, it's not C1. The C1 regularity is completely fine, but when you go into C1 alpha regularity, you will get a worse exponent over there. Yes, but for the Nash, it doesn't matter how many you have, as long as it's finite and as long as it's pointwise finite with a number of terms which only depend on the dimension n, you're completely fine.
Thanks.
So proof. Oh, damn, I'm going much slower. Proof exercise. So cover compactness plus precision of unity. Okay. So the first step is done. Of the heuristic which I just erased, which is given UK, look at the distance of the induced metric to G, decompose it as a sum of primitive metrics. And now what is K? Well, it's exactly the image of, so K will now be G minus UK induced metric of my compact domain omega. So all of the matrices which I want to decompose over here are contained in the compact set K. So I can decompose each of these matrices with a finite number over here which depends only on the set K. In particular, it depends on UK. But as long as I only have a finite number of terms which are non-zero, which only depends on n and not UK, so not on this big set K, I'm fine. So what I want to do, given UK, decompose, this is my set K. I use this lemma over here, or this corollary, to decompose all of these into a sum of primitive metrics. I can write G minus UK star E as AL squared applied to this matrix. It's a smooth function. This is smooth. These guys are smooth. And I have my constant vectors over here, eta L, eta L. And now what I want to do is add spirals for each one of these primitive metrics. And so this is so 1, 4.
Sorry, I might be missing something. Aren't you relying already on the K being in the sim positive, in the positive, non-negative definite matrices? Wasn't that what you wanted to prove?
Say again?
Corollary needs K to be inside of the non-negative definite, right?
Yes, so but I'm assuming I'm starting with a short. Strictly short UK.
Sorry.
So I'm starting with UK, which is strictly short. I want to build UK plus 1, which is still strictly short. No worry. So it's still strictly short. This is a positive definite matrix at any point. So K is nice. So what I'm hoping to achieve with my heuristic, or with decomposing and adding spiral, is the following stage proposition, which I will prove tomorrow, which is the main building block of the proof of Nash's theorem, which is simply how to construct UK plus 1 given UK. We hope to achieve, simply state this and then end it over there. We hope to achieve the theorem or proposition (1.8) stage let U in C infinity, and U is now UK. So I'm thinking about stage is given UK, which I now call U. This is a smooth map, strictly short. Immersion. Any epsilon bigger than 0, and for any delta bigger than 0, there exists a strictly small, short immersion, V. This will be UK plus 1, strictly short. Strictly short immersion. Following three things hold. Well, first of all, I'm not going far away in C0, so I'm less than or equal to epsilon to my map U. Secondly, I'm almost G, so G minus dv tensor dvt dv is less than or equal to delta. It's short, but I'm getting as close as I want to G. And thirdly, I have an estimate because I want to control, I want to see that my sequence converges in C1. So I have a control on the distance or the distance between the derivatives. And the distance between the derivatives is bounded by a constant and then G minus dut du. Okay, this is terrible. Let me write this on a third board. Let me write it here. Sorry about this. Let's see on Thursday who has the vote. Okay, and thirdly, the derivative stays close. And okay, it stays close if U is close to the induced metric. Namely, it's bounded by a constant which only depends on n, and the square root of the distance between the induced metric of U and G for C. Cn. The constant only on the dimension n. Okay? So given UK, I can build UK plus 1 as close to to UK as I want in C0. It's as close to being isometric as I want to any delta. I'm almost G, but I'm still short. And I'm still strictly short. So I can simply repeat this process with a sequence over here which goes to 0 in a summable way. Sequence epsilon which goes to 0 in a summable way. And then I get a sequence of VNs such that they converge to G. And the crucial thing is that the distance between the C1 norm of the they're bounded by the distance of UK to G square root. But this goes to 0 in a summable way. So it's Cauchy in C1. So this is a stage proposition which we want to prove given U decompose, add spirals. Adding the spirals gives V. We just have to make sure that V is short. I mean, it's exactly the heuristics I gave you, slightly different decomposition because here I'm ending up with something which maybe is not short. But it's an easy fix. I just don't decompose the whole G minus dut du, but I leave something over there. I don't add the full, leave a very tiny piece of size delta halves for the next map. And then I iterate this, and this will give me the proof of Nash. Okay, so stage proposition is the main iterative building block, iterating on the stage proposition will give me a sequence which, when choosing epsilon and delta correctly at every k, gives me a sequence which is converging in C1 to a map, final map, which is an isometric embedding because it's going to 0. Yeah, that's it. So tomorrow, first thing, we almost did all the work already, so I gave you the heuristics. I just need to make this a bit more precise, apply the decomposition lemma, which I just erased, and then, yeah, shouldn't take too long. And then I want to see what you can do, or why there is hope to building better isometries. Like this gives me a C1 map. Nash gives me a C1 map. We saw that in C2 we have all sorts of problems. We have non-existence, we have uniqueness in certain cases. We have super flexibility in C1. What happens in between? Can you generate, or can you construct with this method with a bit more care, can you construct maps which are not only C1 but actually a bit more regular? And I want to show you an exponent which naturally pops up. This is Borisov's exponent, and tell you a bit about what we know and what we don't know, and get into the threshold problem about what happens in between these two regions. Okay, so let me stop over here. I'm anyway over time. Sorry for going over time. Thanks very much for your attention.
Well, thank you for the very clear lecture. So maybe we have time for one question, if there's still something you want to ask. Okay, so it seems that we are good for today. So let's thank both Govin and Dominik for these 2 first days of lectures.